These videos cover Chapter 12, the chi-square test. Remember to pause often, do these problems alongside with me. So in 12.1, we're going to be covering the goodness of fit test for a multinomial experiment. So a multinomial experiment can have qualitative data, and here's an M&M example that there are lots of different colors of M&Ms inside a bag of M&Ms, and so maybe we want to know the proportion of each different color. So we're not talking about two different things here or three, we're talking about many. So that's what we're going to be dealing with these goodness of fit multinomial experiments. So we'll have k possible outcomes. So we'll have n independent trials, k possible outcomes, sometimes these are called categories. And so just to remind yourself that when k is 2, that's a binomial experiment. So we're talking about things more than 2, and we're going to be dealing with probabilities, and so those sums of those probabilities do need to equal 1. So let's just look at some examples. So maybe we're comparing to the previous day. A stockbroker records whether the price of a stock rises, falls, or stays the same. So those are the 3 categories. It rises, falls, or stays the same. Maybe we're rating a restaurant as excellent, good, fair, or poor. So we've got 4 different ratings. So that's multinomial. So the admissions office records which of the 6 business concentrations a student picks. So maybe there are 6 different concentrations. So when we have these multinomial experiments, we're going to end up using what's called a goodness of fit, or a chi-squared. And so the symbol for chi looks like this, and we pronounce that chi-squared. So chi-squared test is what we'll be using to determine if the sample proportions resulting from a multinomial experiment differ from the hypothesized population proportions specified in the null hypothesis. So if they differ from what we think they should be, or we hypothesize them to be. So when we're doing the goodness of fit test hypothesis testing, we're going to determine the null and alternative, we're going to calculate the test statistic, we're going to calculate the p-value, and then we're going to make a decision. So these are going to require some different trains of thought than before. So when we deal with a null and alternative hypothesis for a chi-squared or goodness of fit test, we're going to set, there's 2 options here. So you can do this or this depending on the situation. So we'll set all population proportions equal to the same value or equivalent to each other. So let's say the hypothesized proportion amounts would be 0.25. We expect 0.25. So then the null would be that each proportion would be 0.25, and then the alternative we would say is that they are not all equal to that value. In this other instance, maybe each proportion is a different value. We can think about the M&Ms, that maybe there's not the same amount of brown, green, red, etc. So each one is a different value. And so then the alternative in that case would be that they don't equal their hypothesized values. And it is just important to note that all of these in the null must sum to 1. All right, let's take a look at this example here. You believe your friend has been using an unfair 3-category spinner to determine the restaurant choice for the past several years. You conduct an experiment to test the spinner. So, okay, you know, a normal spinner might be a 3-spinner here. So it looks like the category is my choice, friend's choice, and then flip a coin. All right, so this is what happens when we do the experiment. We notice, okay, that these are the frequencies. So our null has to do not with the experiment that we did, but the hypothesized proportion. What do we expect or want or hope, or maybe the correct, if it was fair, would be? So we would want all categories to be the same. We would want each category to be 1/3, right? We would want each one to be equal. And so in this case, it would be that not all population proportions equal 1/3. Okay, so that's how we would specify in this case here. So again, if you want to see it written out. Let's do another example. 1 year ago, and we're going to take this example and continue with this further. So 1 year ago, a restaurant chain gave about a survey about changes to the menu. One question asked them to rate the entrees. These are the percentage responses. So this is 1 year ago. Okay. Now, based to those responses, they made changes. So this is recently. This is what they found recently. At the 5% significance level, we want to determine whether there's change. So we're not there yet, but we are going to do that at some point. So what's going on here? What's the hypothesized value? So the original hypothesized value here is our 1 year ago. And so let's call excellent 1, 2, 3, 4. And so we'll say that the probability, the proportion for excellent would be this. This is what this is the hypothesized value. It's a 0.2. 3 would be 0.45. 4 would be 0.10. And so that then the alternative would be not all population proportions equal their hypothesized values. Okay, so that is how we would take the previous percentages, the previous hypothesized values, to compare that, hey, we want to know the alternative, did something change? All right, and so there you have it here, and it's written out kind of why. So go ahead and give this a try here. It can be a little bit tricky. So remember that we're dealing with the hypothesized values for our null, not necessarily like what the experiment results. So press play when you're ready to see the answer. And there you go. All right, so now let's get into this. So we've learned kind of how to do the null and alternative. Let's do the test statistic and the p-value. So for these, we're going to need Excel. And for the p-value, we're going to use this formula here, the chi-squared formula there. All right. All right, so the test statistic, this is how we're going to do it. And it is going to require an Excel table, all right? So it's we're going to be determining the test statistic, the chi-squared test statistic, using this here, and we're going to set this one up in an Excel table. Okay, so we're going to use an Excel table to calculate this. And our degrees of freedom is k minus 1. To determine the expected value, we're going to multiply the number of trials times the observed, the probability. And then this is super important here. Those are eyeglasses. The test is valid when the expected frequency, so we're talking about this value here, for each category are 5 or more. So if we end up not having 5 or more, we have to make some changes to the experiment. All right. So let's look at this here. So this is the Excel table that we're going to do each time. So I've written it out here and we're going to do some examples. But so in column A, we're going to put the observed value. So this is what's given, okay? And then the expected value, we're going to get that by calculating n times the probability that they give us. Okay, and then we're going to check the expected values and make sure that they're more than 5. And then from there, we're going to work towards getting this value. Remember, we want O minus E, and then we want O minus E squared, and then we want O minus E squared divided by E, and remember that comes from that formula there, and then we need the sum, so we'll sum that column, and then that's going to give us our test statistic. Okay. All right, so let's go ahead and do it with this one here. So let's put this in here. So we're going to have our observed, our expected, our observed minus our expected, observed minus expected squared, observed minus expected squared divided by the observed there. Okay, so now let's just kind of fill in here. We're dealing with, and I'm going to add the ratings just to help us out here. So we've got excellent, good, fair, and poor. So what is the observed? What do we observe happen? So this is what they gave us a year later. Observed, we observed 83, 105, 16. So those come from here. These are our observed, what we see in the experiment. Now, expected gets built from our previous probabilities, so that's these, times the n, how many people we actually are going to be asking. So if here we can see that our n is 250. So for excellent, it's going to be 250 times 0.15. And here it's going to be 250 times 0.30. And here it's going to be 250 times 0.4, times 250 times 0.45, and 250 times 0.10. All right, and then now we can just let Excel do its magic. Observed minus expected, and then drag it down. And then we want to take, let's pause here and make sure everything in this column needs to be greater than 5. We're all good, so we'll keep going. This, we want to square it. Drag that down. This, we want to take what's squared and we want to divide it by its expected value and drag that down. And now from this column, we can get the test statistic by summing this column here. So our test statistic is 6.52. Our test statistic, chi-squared test statistic, is equal to 6.52. And that was the only direction here. Calculate this test statistic. So this is the test statistic. And here it is written out if you want to make sense of that a little bit more. We're going to pause here, and in the next video, we're going to determine the p-value for this example and continue on with a few more examples.